In the summer of 1990, the first images came back from the Hubble Space Telescope, and they were blurred. The primary mirror underneath was one of the most precisely polished objects ever manufactured, smoothed to a fraction of a wavelength of light. It was also ground to the wrong shape, off by 2.2 micrometers at the rim, roughly a 50th the width of a human hair. But the mirror was not where the failure happened. The instrument built to verify that mirror had been assembled 1.3 millimeters out of position. Every reading it gave was wrong, and the people polishing trusted it completely. You are watching Trade Archive. If you spend your working life inside a thousandth of an inch, subscribe and drop a like before we start, because this one sits underneath every drawing you have ever cut apart from. Stockholm Harbour, August 10, 1628. The warship Vasa cleared her moorings on her maiden voyage, sailed roughly 1,300 meters, heeled over in a gust, and went down in the channel. Around 30 of the 150 people aboard drowned. She sat in the mud for 333 years. When the Vasa was raised and archaeologists finally began measuring her timber by timber, they found a hull that was not symmetrical. The port side and the starboard side did not match. Among the artifacts recovered from the wreck were the carpenters' own folding rulers, and those rulers did not agree. Some were divided into Swedish feet of 12 inches. Others were Amsterdam feet of 11 inches. Men working on opposite sides of the same warship were laying out frames against different definitions of a foot, and neither crew had any way of knowing. That is the world before tolerance. Not sloppy work. The joinery in the Vasa is superb. It is a world where every craftsman is accurate to his own standard, and no two standards are the same. For most of manufacturing history, that did not matter, because nothing was meant to be swapped. A musket lock, a clock movement, a pump, all of it was handmated. There was a trade for it. The fitter took the parts as they came off the forge, offered them up to each other, and cut metal until they seated. Every assembly on the bench was unique. The file was the most important tool in the building. As late as the turn of the 20th century, almost every part arriving at an assembly line still needed a file taken to it somewhere. A broken part was a catastrophe. You could not order another one. You sent the machine back to a craftsman who made a new part to suit that machine and no other. The pressure to break it came from artillery. In 1765, under a royal order, General Jean-Baptiste Vaquet de Gribeauval began standardizing the French artillery train, boring gun tubes to controlled dimensions so that ammunition could be made to a common size and carriages could share components across a battlefield. An army that can only feed each gun its own bespoke shot does not have artillery. It has a collection of individual cannon. The first man to carry that thinking into small arms was a French gunsmith named Honore Blanc. On July 8, 1785, at the Château de Vincennes outside Paris, Blanc laid out roughly 50 musket locks in front of an assembled group of officials and diplomats. He took them apart. He mixed the components together in bins. Then he pulled parts out at random and built about 25 working locks in front of them. He was working with gauges, filing jigs, and master models, holding parts to a standard rather than to each other. One of the men who saw the implications was the American minister to France. Thomas Jefferson wrote back to John Jay, describing an improvement in the construction of muskets in which every part was made so exactly alike that what belonged to one could be used for every musket in the magazine. He noted the advantage plainly. When arms need repair, it is evident. Jefferson did more than admire it. In November 1790, he forwarded a memoir from Blanc directly to Secretary of War Henry Knox, trying to get the method, and the man, transplanted to the United States. Blanc's own trade destroyed him. The gunsmiths of France understood exactly what a system of gauges and jigs meant for men who made their living by hand-fitting, and they opposed him. The French state let the method lapse. The idea crossed the Atlantic and landed in the American armories, and it took decades longer than anyone promised. Writing to James Monroe in November 1801, Jefferson described a process in which the pieces of a lock were made so exactly equal that 100 locks could be taken apart, their parts mingled, and 100 locks reassembled from whatever came to hand. He also noted in the same letter that Blanc had invented a similar process in France more than a decade earlier, and that the improvements he was describing had not yet been extended beyond the lock. Eli Whitney signed a contract with the United States government in 1798 to deliver 10,000 muskets. A year in, he had delivered none. The last of them arrived in January 1809, roughly 8 years late. The muskets that survive from his shop carry match marks cut into the parts, the small identifying scratches a fitter uses to keep a specific lock plate with its specific tumbler. You only need match marks when the parts are not interchangeable. Historians who have gone through the surviving arms and the correspondence, Merritt Roe Smith and Robert Gordon among them, concluded that the demonstration Whitney staged in Washington in 1801 was done with specimens prepared for the occasion. The man who actually did it worked 60 miles up the Potomac. John Hancock Hall took a contract at Harper's Ferry to manufacture his own breech-loading rifle, the Model 1819, at the Rifle Works on Lower Hall Island. He spent years and more than $150,000 of government money building water-powered machine tools before delivering rifles in quantity, and the armory superintendent regarded him as an expensive eccentric. What Hall was building was not a rifle. It was a system of more than 63 inspection gauges, a physical definition of every critical dimension on the weapon, sitting where any workman could reach it. In December 1822, Hall wrote to Secretary of War John C. Calhoun that he had succeeded in establishing methods for fabricating arms exactly alike and with economy by the hands of common workmen. In 1826, a government commission tested that claim and confirmed it. Simeon North was building the same rifle at Middletown, Connecticut, and parts from the two factories interchanged. That is the moment. Not one shop achieving consistency, but two manufacturers hundreds of miles apart whose output could be mixed in a crate. Hall did it with gauges because there was no other way. And a gauge does something a dimension on a drawing cannot. It does not tell you the size. It tells you whether the part is acceptable. The go gauge must enter. The no-go must not. Between those two objects lies a range of sizes that will work, and the workman does not need to know what that range is. He needs to know the part passed. That is tolerance, embodied in steel before anybody could write it down. Writing it down came slowly. Through the 19th century, a drawing typically carried a nominal dimension and an expectation that the shop would work to it as closely as the shop could manage. The engineer specified perfection, and the fitter delivered whatever the file left him. The knowledge to close that gap existed, but it lived in men rather than on paper. Feeds, speeds, tap drill sizes, which fit to use where, all of it was apprenticeship property, passed down a bench at a time, and guarded because it was the thing that made a tradesman worth hiring. The trade journals pried it loose. American machinist and machinery ran the numbers, the practices, and the arguments out into the open, and in 1914, the first edition of Machinery's Handbook collected the lot between two covers. A shop in Ohio and a shop in Glasgow could now look up the same tap drill and get the same answer. Around 1902, the Null Engineering Company in Britain published a formal system of limits and fits, one of the first attempts to put the permitted range on paper as policy rather than as a note to one workman. Shaft basis, hole basis, running fits, press fits, all of it turning the fitter's judgment into a table. But a table of limits is worthless without a physical standard to set your gauges against, and until the end of the 19th century, the physical standards were the problem. Henry Maudslay had built a bench micrometer in his London works that resolved to a 10,000th of an inch, and the men in that shop called it the Lord Chancellor, because when two workmen disagreed about a measurement, its reading was the final court of appeal. That was one instrument in one shop. Joseph Whitworth, who had served his time under Maudslay, went after the underlying problem. In 1840, he presented a paper on plain metallic surfaces, describing the three-plate method, which is how you produce a true flat when you have no true flat to copy. You cannot lap two plates together and get flatness, because two surfaces will happily wear into a matched convex and concave pair. Bring in a third, work all three against each other in rotation, and the only geometry all three can share is a plane. It is the closest thing engineering has to conjuring accuracy out of nothing, and it is still how scrapers are taught. In 1841, Whitworth proposed a standard screw thread, a fixed 55-degree included angle with rounded crests and roots and a defined pitch for every diameter, and pushed British industry onto it. By the Great Exhibition of 1851, he was showing a measuring machine that resolved to a millionth of an inch. Then, a Swedish armory inspector took the physical standard out of the laboratory and put it in a wooden box on a shop bench. Carl Edvard Johansson worked as an inspector at the Carl Gustaf rifle factory in Eskilstuna. His problem was that setting gauges required a reference, and references were expensive, scarce, and belonged to somebody else. Beginning in 1896, he ground hardened steel blocks to precise lengths, rough cutting at the factory, and doing the finish work at home on his wife's sewing machine, which he had fitted with a grinding wheel. His Swedish patent for gauge block sets was granted on May 2, 1901. What made them extraordinary was not the accuracy alone. The blocks were finished so flat and so smooth that when two were slid together with a light twist, they rung. They stuck, hard enough to lift a stack by the top block, held by molecular adhesion. That meant a set of 102 blocks running from 0.5 to 300 millimeters in steps of 0.01 millimeters could be combined to build essentially any dimension a shop would ever need, from a box you could carry under one arm. The English patent followed in 1902. What that box changed was not the laboratory. It was the shop. Before it, a firm that wanted to set a go gauge and a no-go gauge sent work out to a national laboratory or a large customer's standards room and waited. After it, a tool room stacked blocks on its own bench, set its own gauges against a length it could prove, and knew that a shop 1,000 miles away stacking blocks from the same system would land on the same number. The first set to reach the United States went to Henry Leland at Cadillac around 1908, and Leland, who had come out of the Springfield Armory tradition and understood exactly what he was holding, said there were only two people he took his hat off to. One was the President of the United States. The other was Mr. Johansson from Sweden. Henry Ford eventually bought the company outright, and Johansson spent 13 years working in Dearborn. By the 1920s, the tools existed. A shop could hold a size, prove a size, and write the permitted range on a drawing. And the industry promptly discovered that it had solved the wrong problem. Because size is not the only thing that has to be right. Take the simplest case in the trade: a plate with 4 holes in it, and a mating plate with 4 pins. The drawing calls out the hole diameters with limits, and it locates each hole from the edges of the plate with a dimension and a plus or minus tolerance. Half a thou either way in X, half a thou either way in Y. That is coordinate tolerancing, and it is how drawings were dimensioned everywhere. Now think about what that permits. A hole 0.0005 high and dead on in X is accepted. A hole 0.0005 high and 0.0005 over in X is also accepted, because both dimensions are inside their limits. But that second hole is farther from where it should be. The zone you have drawn is a square, and the corner of a square is 1.414 times farther from the center than the middle of its side. The hole does not care about squares. A hole is round, and a pin going into it is round, and what determines whether the thing assembles is the radial distance from where the hole should be to where it is. The square zone accepts parts at the corner that are further out of position than parts it rejects along the axis. Run the numbers on it. A zone of plus or minus 0.005 in both directions is a square 0.010 on a side, with an area of 0.0001 square inches. The circle that contains that square, the one that accepts every part. The square accepts, has a diameter of 0.014, and its area is roughly 0.000154 square inches. Same worst-case deviation, about 57% more acceptable parts. That is the whole argument. Not a looser tolerance. The same functional limit, described with a shape that matches the function instead of a shape that matches the drafting convention. Every part in that extra 57% was a good part, and under coordinate dimensioning it went in the scrap bin or came back through the inspection department for a deviation approval that took a week. The man who worked that out was a British inspector named Stanley Parker, and the documentary record of him is thin enough to be frustrating. What is on paper is this. In 1940, at the Naval Ordnance Inspection Department Gauge Factory in Sheffield, Parker was working on the problem of dimensioning for inspection. His foundational report, Notes on Design and Inspection of Mass Production Engineering Work, was issued that year by the Gauge Design Drawing Office at the Naval Ordnance Gauge Factory in Sheffield, and a copy sits in the National Archives. The problem in front of him was a war problem. The Admiralty needed the production of a naval weapon expanded rapidly across a number of contractors who had never built it, firms with their own shops, their own inspectors, and their own reading of a drawing. Parker's method was applied to redimensioning and retolerancing that weapon's drawings so the work could be spread. When a drawing goes to 6 shops instead of 1, every ambiguity in it becomes 6 different parts. The work moved up through the machinery of a country at war. In 1942, an Admiralty committee took it on, chaired by F.H. Rolt of the National Physical Laboratory, the metrologist who had met Parker at the Sheffield Gauge Factory 2 years earlier. In 1944, it went wider, to an inter-services committee covering all 3 branches. In 1948, His Majesty's Stationery Office published the result as Dimensional Analysis of Engineering Designs. From a wartime inspection problem to national policy took 8 years. Parker was awarded the British Empire Medal in 1945. The Admiralty gave him a substantial monetary award in 1950. He sat on the British Standards Institution subcommittee that wrote the 1953 revision of BS 308, the first British drawing standard to carry geometric methods. In 1956, he published a book, Drawings and Dimensions. And here is the part that gets forgotten. Parker used no symbols, not one. The system was originally written out in words and ordinary notation. The symbols came later from other people, in other countries, and they are what the trade now calls GD and T, geometric dimensioning and tolerancing. The wall of boxed feature control frames in the corner of every modern drawing is the shorthand somebody else invented for what Parker wrote in sentences, which is where it turns into a standards fight. The Americans went at the same problem from the manufacturing side. In 1946, United States Army Ordnance issued ORD 30-1-7, which introduced symbols rather than written notes. The Society of Automotive Engineers put out an aeronautical drafting standard the same year. In 1949, the military consolidated it into MYL-STD-8, and in 1953, MYL-STD-8. A codified what the trade now calls Rule 1, the envelope principle. A feature at maximum material condition must have perfect form. If a shaft is at its largest allowed diameter, it has to be straight and round because there is no clearance left to give it anywhere to bend. The commercial standards followed the military ones. The American Standards Association issued Y14.5 as a dimensioning standard in 1957, revised it in 1966, and the standard was issued under its own designation as ANSIY 14.5 in 1973. ASMEY 14.5M in 1982 is the one most shops treat as the arrival of modern practice. Then 1994, then 2009, then the current 2018 edition. In Britain, BS 308 ran through revisions in 1964, 1972, and 1985, before being withdrawn in 2000 in favor of BS 8888 and the ISO system. Internationally, the work went into ISO 1101, which became the reference for geometrical tolerancing outside the American system and is what most of the world's drawings now answer to. Two committees, working the same problem, publishing in parallel for decades. The American who drove it for 45 years was Lowell Foster, a tool designer who ended up chairing both the United States National Committee and the ISO Committee. His geometrics books, first published in 1970, are the reason a generation of American engineers learned the symbols at all. But the ISO track and the American track had made a foundational decision differently. ASME kept the envelope principle. ISO worked from the principle of independency, where size and form are separately controlled unless you say otherwise. The same drawing, read in a Detroit inspection room and a Stuttgart inspection room, could produce two different verdicts on the same part. Foster's own position by 1994 was that the systems agreed on the overwhelming majority of cases. Others in the field argued the disagreement ran through a substantial fraction of everything you could specify. And this was not academic because the trade had already learned what a definition mismatch costs in the middle of a war. British industry ran on the Whitworth thread. American industry ran on the American National Form, which came out of the Sellers system. Whitworth used a 55-degree included angle with rounded crests and roots. The American form used 60 degrees with flat crests. Even where the pitches nearly agreed, they did not agree. At half an inch diameter, the British coarse thread was 12 threads per inch, and the American was 13. Now put two Allied armies in the same theater, sharing depots and repairing each other's equipment. When Packard built the Rolls-Royce Merlin under license in the United States, the fastener question alone consumed serious time because Packard's shops worked in Sellers threads and the drawings did not. A bolt is the cheapest thing on an aircraft. It is also the thing that stops one flying when the only bolt in the crate will not start in the hole. The fix took until November 1948, when the United States, Britain, and Canada agreed the unified thread standard. The British accepted the 60-degree angle. The Americans accepted rounded roots. Both sides gave up something they had built an industry around, because the alternative had already been demonstrated. Which brings us to the second half of the problem Parker opened, and the one that causes more argument on a shop floor than position tolerance ever has. Where do you measure from? A part has 6 degrees of freedom. It can translate along 3 axes and rotate about 3 axes, and until you take all 6 away, it is not sitting anywhere in particular. The way you take them away is with datums, in a specific order. The primary datum surface goes down on the plate and locks 3 degrees, 1 translation and 2 rotations. The secondary takes 2 more. The tertiary takes the last one. Prime the part against 3, then 2, then 1, and there is exactly 1 way it can sit, and every inspector who follows the drawing gets the same answer. Before that was written into drawings, reference surfaces were implied. The dimension came off an edge, and which edge, and in what order, and how the part was clamped while it was measured, all of that lived in the head of whoever was doing the work. 2 competent inspectors, working from the same drawing, with calibrated instruments, in good faith, could measure the same part and disagree. Not because either was wrong, because the drawing never said what the part should be measured from. The practical version happens every week. A machined casting comes in with a rough face and 3 finished pads. One inspector sets it on the pads because that is how it bolts down in service. The other sets it on the largest flat area because that is what the surface plate wants. The part passes on one bench and fails on the other, and 2 companies spend a fortnight arguing about a part that was correct the whole time. The datum call-out is the sentence that ends that argument before it starts. If you want to know what an unstated reference is worth, look at what happened in the Rhine. In the early 2000s, German and Swiss crews were building a bridge across the High Rhine at Laufenburg, working toward each other from opposite banks. Germany references elevation to the North Sea. Switzerland references the Mediterranean. The 0 points of those two national height systems differ by 27 centimeters, and both engineering teams knew it. The correction was calculated and applied. It was applied with the wrong sign. Instead of canceling the 27-centimeter difference, the correction doubled it. The two halves were being built toward a meeting point 54 centimeters apart in elevation, and nobody found it until the spans came close enough over the water to compare. The German side had to be brought down. Nobody was hurt. No instrument is out of calibration. Every measurement taken on that project was accurate. They were accurate to two different definitions of 0. The modern version of the same failure runs through a computer. In 2006, Airbus was assembling the A380 from major sections built across 4 countries. The wiring is the nervous system of that aircraft. Roughly 530 kilometers of wire, more than 100,000 individual wires, and around 40,300 connectors carrying over 1,100 separate functions. All of it bundled into harnesses that have to be manufactured to length and then threaded through an airframe assembled somewhere else. The design offices in Germany and Spain were working in CATIA version 4. France and Britain had moved to version 5. The two versions did not calculate the geometry of a bent cable the same way, and a wire routed through a 3-dimensional airframe accumulates that difference over every bend. The harnesses came out too short. Not by a margin anybody could stretch out on the floor. Thousands of them, in an aircraft with no room to reroute. The airframes were correct. The wiring was manufactured correctly to the model it came from. The models did not agree. Airbus's parent company told investors the delays would take 4.8 billion euros off profits over 4 years. The chief executive resigned. The first aircraft went to Singapore Airlines in October 2007, roughly 2 years behind schedule. And in 1999, the definition problem reached Mars. The ground software supplying thruster performance data to the Mars Climate Orbiter navigation team produced its figures in pound-force seconds. The navigation software consuming those figures expected Newton seconds. The two units differ by a factor of about 4.45, so every trajectory correction the team calculated was based on a number that was wrong by the same ratio, consistently, all the way from Earth. A correction on September 15th was intended to put the spacecraft at an arrival altitude of about 226 kilometers. It arrived at roughly 57 kilometers, well below the altitude the structure could survive, and was destroyed on September 23rd. The mission cost $327.6 million, of which about $125 million was the orbiter itself. Every one of these is the same failure. Laufenburg, the A380, the Mars orbiter, and the Vasa, 375 years earlier. Nobody was careless. In all of them, two groups of competent people worked accurately to definitions that did not match, and nothing in the process was designed to catch the disagreement. Which is the entire point of what the standards committees built. A tolerance is not permission to be sloppy. It is a contract. It says, here is the nominal. Here is the acceptable variation from it. Here is the geometry of the zone that variation lives in. And here is the reference frame the whole thing is measured from. Once all 4 of those are on the drawing, the shop and the customer are arguing about a part instead of arguing about what the drawing meant. And the system pays the shop back for its honesty. Take a hole with a permitted range from 0.500 to 0.510, positioned within a zone of 0.010 at maximum material condition. Maximum material is the condition where there is the most metal left, which for a hole is its smallest size. Drill it at 0.500 and you get the 0.010 you were given. Drill it at 0.506 and the hole has 0.006 more clearance in it than the drawing assumed, and that clearance is real. A larger hole will swallow more misalignment from the pin going into it. so the extra 0.006 is added to the position tolerance as bonus, and the zone becomes 0.016. Nothing was given away. The drawing hands back as much freedom as the assembly can physically absorb, and not a tenth more, because the geometry of the fit is doing the arithmetic instead of a draftsman guessing. And all of it can be checked with a fixed functional gauge, a piece of hardened steel with pins standing at the virtual condition positions. The part drops on, or it does not. No interpretation, no argument, no inspector's judgment on a Friday afternoon. That is Hall's go gauge, 200 years on, with the geometry finally written down. Which brings us back to a mirror. The Hubble primary was polished against a reflective null corrector, a device whose whole purpose was to define the correct optical shape. During its assembly, a technician set the spacing of a lens using a laser reflected off the end of a metering rod. The laser landed on a chipped spot of paint on the rod's end cap rather than the rod's actual end surface. The lens ended up 1.3 millimeters out of position. The consequence of that specific 1.3 millimeters accounts, in full, for the aberration measured in orbit. The Government Accountability Office put the expected cost of the telescope at more than $1.5 billion. 2 other test devices flagged the problem before launch. An inverse null corrector and a refractive null corrector both showed a discrepancy. Both were set aside because the reflective null corrector was the more accurate instrument and the team trusted the more accurate instrument. That is the failure. A correct measurement taken faithfully against a reference that nobody had verified by people who had every reason to believe it. The mirror was polished to superb accuracy. It was accurate to the wrong definition of correct. It took the Space Shuttle Endeavour and 5 spacewalks in December 1993 to install corrective optics and fix it. And the fix worked because engineers on the ground could describe the exact shape of the error to a precision that let them grind glass to cancel it. The whole history of tolerance is the history of one question that will not go away. Not how accurately can we make this. We got very good at that a long time ago. The question is, how do 2 people in 2 buildings holding 2 instruments prove they are talking about the same thing? The next time you look at a feature control frame and think it is bureaucracy, remember that everything in that box exists because somebody, somewhere, made a perfect part that did not fit. If this is your trade, subscribe to Trade Archive and give the video on screen a watch.